Hello everybody, I would like to make a short screencast about Bayesian Deming regression paired together with the Mahalanobis distance testing so that we can just analyze and make some meaningful affirmation about a very small data set of only 7 samples. And the data set itself is a real one, it's not simulated. The ownership is from my institution, which is SSMT Vocational High School in Locarno for lab technicians, and is given us courtesy. Here there is some links, interesting links. You have a 2021 publication where I just already published this Mahalanobis distance method, and then there is the 3 other one, and they're talking about Bayesian Deming and this ability to perform Mahalanobis distance even in some more difficult conditions. The data set itself is a real-time PCR experiment, so we have those numbers are estimated cycle at which the sample turned out to be positive. And X and Y were just 2 different kits to prepare this real-time PCR. So we want to assess if those 2 kits are equivalent or not, and the back idea is to hope to reject this idea. So we want to reject, and we want to say that one is better than the other, or it's at least different. So the null hypothesis is slope equal to 1, intercept is equal to 0, but this has to be rejected. And of course X and Y both contain some error component because they are measurement, so it's not possible to go with a linear regression, a classical one. So we need to go to Deming regression or any other total least square method, or just try the very brand new method, which I will show you how powerful it is. So quickly we go through data. And as you can see, we have 7 points, and among them 2 are probably outliers. So we have an additional problem, and we have 7 data points, but 2 of them are outliers. I've numbered them here so that we can see that the row number 3 and row number 5 are problematic. So just to see how classical method fail, we can load up the MCR library and perform a Deming regression with analytical confidence intervals. And if you do it, you see that the confidence intervals are very wide. So we have a slope from 0.23 to 1.79, and remember our null hypothesis is 1, and we want to reject it, not to accept it. So this is absolutely impossible to do that. And the same for intercept, which minus 35 to 20, and our null hypothesis is 0. It's sitting right in the middle, and it's a very wide, for both we have very wide confidence intervals. We can also plot the Deming regression, and you see how wide these confidence intervals are. And of course we can perform also the regression removing these 2 outliers. So I have done it here. I removed 0.3 and 0.5, but running again on this cleaned up data set reduces of course the confidence interval, but not that much. They are still very wide, and it's impossible, really impossible, to reject the null hypothesis. And the very same, actually even worse, happens if we use the brand new equivariant passing Babylog algorithm, which should be robust, so it should tolerate better these 2 outliers. But in this case, running on this data, we get a completely meaningless result. You see, okay, we have slope 1, but the confidence interval goes to negative for the slope, so there is no safety to say even if the slope is really positive or negative. This is really a meaningless result. And even if we take the data without outliers, so the only 5 points here that we have cleaned up also for the Deming, you see that the confidence interval are very wide. and we are blocked there because there are no other alternatives in a classical way. It's not possible to perform jackknife, confidence interval, or even make a bootstrap experiment because the sample is too small to make any bootstrap experiment. So let's then move to what really is important today. So we have to show how this Bayesian Deming has superpowers, especially when we are dealing with very small sample sets. So we have to load up the libraries. This is a very brand new library which makes this Bayesian Deming method available. You really need CRAN 431 or better than that, or newer than that, because it's a new library. And you also better load up RStan, which is used for the summary of the results. And I also set a seed so that you may try to get exactly the same results as mine, but this is with RStan, it's known that even if you set the seed, it's not necessarily the case. So I am also using Linux, and I have Debian operating system, so it's not necessary, so that even if you try to use this, that you will get exactly the same results, but you will get very similar results anyway. So I set seed, and then I just run the sampling. You see, this is a classical sampling. We have a warning. This should not make too much scare. Should not scare the user. When you get such a result, you better check the result with traceplot. And with traceplot you can check the sampling, but you see there is good convergence, there is no strange things, the chains are mixed quite nicely, so we can pretty much ignore this warning. This is just only a warning, and we can just look at the result, and the result is that even in this case we have very wide confidence intervals. And then you say, okay, we are blocked. No, this is a but here. This is very important. Let's first take a look at the plot we get. You see that with the confidence interval here, this light blue zone, we have the sensation that the identity line is really parallel running, but it's higher. So we may suppose that there is an intercept difference here, but we cannot get it from these values here, from the confidence and from the classical confidence interval. I told you but because being this Bayesian method, actually what we have done is to get a posterior sample, and in this case we have per default we have 4,000 samples pairs. They are pairs of slope and intercept. They are paired. And because of this reason, we can plot those points in a two-dimensional plane, and we can make a correlation matrix. We can calculate a correlation matrix, and then we can calculate the distance from the center of the correlation matrix to the null hypothesis position. And that's what basically Mahalanobis distance testing is. And to do all this, actually it's just a matter of calling one single function, which is this one, which is already prepared in the package, which is probably the most important function in the package. And if you click on that, you get this very informative plot. In this very informative plot you get very many elements. So you have the box here, the violet box, which are the confidence intervals, a bit like those. Actually those in violet, they are calculated with the highest density, and those are with the symmetric one. I want just to make both confidence interval available, but as you can see, the difference are very minimal. You can compare them. But this is not only the only element. The cross here, red cross, is our of course our null hypothesis, but this is the cloud of 4,000 pairs of intercept and slopes, and as you see, it's possible to calculate the covariance matrix, and those ellipses here are just the ellipses of the probability of 95 and 99% of the covariance matrix. So we can assess the distance from this point to the center of this covariance matrix, and this distance is a Mahalanobis distance, and the Mahalanobis distance is the chi-square distributed with the degree of freedom that corresponds to the number of different dimensions. We have only 2 dimensions, so we have to test against degree of freedom 2, and this distance in this case is about 6 multiplied 6 elevated minus 11. So we have a very small probability that this null hypothesis could be compatible with those data. So we can really, about this probability, we can just reject the null hypothesis in a very safe manner. Usually I suggest to use a 99 test instead of a 95 test, but you have to read my paper in 2021 to see why this can be a good idea. And we can also see that the biggest shift is on the intercept, because the major distance is on this axis. This is the main reason why the 2 methods are not equivalent, because on the slope instead the difference is pretty limited. This is the center, and violet is the center of actually the violet cross is the mean of slope and the mean of intercept, and in blue you have the center of the cloud, so this is actually the real distance. They can be slightly different, but usually they are very much overlapping, the two center positions. And well, this is something that is not possible to do with any other method, because it's not possible to generate such a cloud via bootstrap. It would be, but with a sample size of 7 it's not possible, and that's why the Bayesian Deming has really, in my opinion, superpowers, especially when you are dealing with small data sets. Take-home messages with such a small sample size is absolutely impossible to do almost anything, at least with conventional regressions. Mahalanobis distance is very powerful, but needs somehow to generate those clouds, and those clouds can be generated either with Bayesian methods or with the bootstrap methods, but both of them, bootstrap methods, are not available on small data sets. In this case it's only Bayesian method possible. And in general, this Mahalanobis distance, as I wrote already in 2021, they have an enhancement factor of at least 1 to 5 for the power. I mean, a data set of 40 samples can have a similar or even a higher power than a 250 sample data set, given the fact that you are just testing with the Mahalanobis distance instead of the classical confidence intervals. But you can read it in my archive paper. This has already been assessed 3 years ago. Okay, I think it's all. I hope that you can stop eventually the video and read the text if you are more interested. And that's it for today.